Okay, let's begin with a recap. The goal of structure prediction is essentially to predict the three-dimensional structure from the sequence. If I take a sequence, a stretched out amino acid chain, and throw it into a solvent, then it develops a unique three-dimensional structure. So the protein does it in solvent, but it's difficult to compute that. Do you remember the reasons why it's difficult to compute that? If the protein can fold, as it is called, so find its unique three-dimensional structure from a stretched out amino acid chain. Why is it so difficult for us in the computer to do the same thing? Anybody here can say anything why it could be difficult? It's very difficult in terms of computation, but just why? Is there any problem that somehow you know is not that easy that immediately maps to this kind of problem? So imagine you have a stretched out chain of pearls. 1, 2, 3.
N goes in the point of joining.
N goes, sorry? N goes in the hundreds, yes?
N goes that we may turn the part in the point of joining.
I still didn't get it.
In the point of joining, we may turn our parts on different angles.
Yes, we can turn, we have different angles, but what I mean is in regular physics, in regular everyday life, or the types of typical physics problem, can we model how the Earth rotates around the moon? The moon rotates around the Earth. Can we model that? Totally easy. Can we model how the Earth rotates around the sun? Totally easy. Can we do sun, moon, and Earth? No. This is no longer trivial. So this is the problem, the three-body problem is already not analytically solvable easily. So now there are hacks. Even for this simple problem, there are issues, right? Now we talk about hundreds of residues. Each of these has about tens of atoms, and this all moves around in water, in solvent. This is a highly non-trivial problem. Okay? Now let's get back to chemistry. Let's get back to, I take a simple chemical molecule with just the kinds of things that make up drugs. Typically in the ballpark is just typically a single molecule, or relatively small molecules, or relatively small compounds at best, with maybe tens of molecules. Now I have one, and I want to compute whether this one docks the other one. So I have two small molecules. Each of these is 100 times smaller than a protein. Can I do that in a computer? Do you believe? Can chemistry essentially dock molecules? So even that is not easy. Even for that, the experimental way sometimes is easier. What chemistry can do is, once we have found a solution, optimize the molecule. So how can I sort of imagine that the binding could be strengthened? And that it may tell the chemist how to improve the binding, affinity of binding, or the stability of binding, or whatever he or she wants to maximize. But even for small molecules, this is a problem. Proteins are big, okay? It's much, much more difficult. That is the problem here. Now, the problem is, as was said here before, is ultimately one of CPU time. And maybe at the moment is one of the CPU time. But it's unclear at the moment whether part of the problem is simply in the inaccuracy with which we build the underlying potentials, so the types of forces. These forces that we use, they always assume some constants. So for instance, for the movement in water, you need a dielectric constant. You may have heard that in your physics at school. There's a dielectric constant for water. But that's an average. And that's an average that is true as long as water is isolated. The dielectric constant is no longer true when you have a protein in that solution. And in fact, the dielectric constant is different where in the protein you look. So you cannot even treat water. I mean, all the simulation, molecular dynamics simulations treat water as a background. But in principle, even that is limited accuracy. And maybe the faults by the size of the molecule, the faults that come from these mistakes, maybe ultimately they will prevent us from doing it even if we had all the CPU time in the world. Okay? So this is really a hard problem. Proteins can do that. And one reason why we believe proteins can do that is we believe there is something that is often referred to as a rapid collapse. So you have this long stretched out chain that is insolvent, and then there's immediately a collapse. So instead of this long extended chain, you now have much shorter units. And this rapid collapse most likely helps to find the minimum, low energy minimum, very quickly, to make proteins fold in the times that are needed. One way in which we can predict 3D structures is by comparative modeling. Comparative modeling means I have a protein for which I experimentally know the structure, and another one for which I do not know the experimental structure, but I see that these two have the same sequence. And I forgot to switch on my... Have you switched it on? The camera? Oh, fine. Sorry. Thanks, Dimitri. So we essentially look up the experimental structure because we have a protein that is sequence similar. How do I compare sequences? Can you name some algorithms or some concepts how to compare protein sequences? Pairwise sequence alignment is an answer, and that in fact, again in the examen at the end of July, we appreciate shorter answers, so we discourage writing entire pages, and sometimes, just a sec, sometimes this may just be enough as an answer. But in a question like explain the idea, you may want to have to say more, yes? Progressive iterative alignment. So now we get into the world of keywords, buzzwords. This is absolutely true what you say, but my question now is, what do they mean? How would you compare to sequences? These are right answers. But do you have an idea how you would write the algorithm for it? Is any algorithm coming to your mind that we discussed? Yes?
I mean, for example, sideblast, right? So you just take two sequences, for example, starting with two sequences, and then using this scoring table to compare them if they have similar structures. And yeah, and using this scoring table, you can calculate weight, a score for that structure if they are similar or contain similar, or if they are same or similar. And do this iteratively.
Okay, so the word was Psyblast. Just repeat what you said. And I believe this would be the kind of answer that we would accept. Although in principle, if I wanted to test understanding, I would not be quite content. So let me say a few things that were said. So the statement was Psyblast, and Psyblast begins by taking a sequence and comparing the sequence against the scoring table. Technically, this is correct. But I'd actually like you to explain a little bit what you mean by the scoring table. What is this table scoring? And then you said, and then we assess how well, using the scoring matrix, how well this sequence fits to the structure. Again, everything you say is right. In detail, however, what you do is you're not fitting a sequence to a structure. We're actually comparing two sequences. It is true that for one, you know the structure underneath. But at the step of comparing the two, in the two sequences, you do not know the structure. You do not actually typically use the structure. You can. But then you have to a little bit explain what's the idea. How could you possibly use the structure would then be the question. Now back again to the word of pairwise alignment. How do I know? You already said it. So I assume that in the exam you can give the answer. But this is very essential for everybody in this room. I'm not saying that this question is going to come, but this is the kind of question that has come almost in every single exam of this type. or questions around these kind of questions will be asked, that's very clear. And these you should be able to relatively quickly and clearly answer. Again, for pairwise alignment, what's the idea? Scoring matrix is the right word, but even before you begin with the word scoring matrix, yes?
Some matches, sequence matches are like worth more than other sequence matches.
Yes.
This scoring matrix helps numerically quantify.
That is correct. The scoring matrix helps you to numerically quantify what is an important similarity, and because it helps you, somehow there are different ways of scoring matrices. Some are better than others. This is all correct. But before we get into the idea of scoring matrix, you have two strings, two words, two very long words. How do you compare them? Before you ever use the term scoring matrix. And I take it you already said it and you know more. I want somebody else.
Do you mean global approach?
No. So yes, so this is, again, those are important buzzwords. Local versus global, very important. And often it is enough to drop those buzzwords. But now we are at the level of letters, at the level of long words. How can I compare them? Yes, we are talking about proteins in the background, but when I compare two words, actually, I don't really need to talk about words. How can I compare two strings? You know that from computer science. That's the simplest way of doing it.
Character by character. Character by character from character.
Character by character, at a distance, yes, exactly. Character by character. But character by character will give you essentially one superposition of the two, and then you will compare character by character. But then you slide on or what? Right? And that is, in fact, if you did that one by one and tried all possibilities, then the space is too huge. So that brings us to the issue of dynamic programming. And again, somehow the idea of the dynamic programming idea, you should have that, you always assume that I and j, what happens at the next position, is independent of each other, and that you always can sort of find the optimal path to a different point, and then you have actually an n square type of order n square problem, where n square is the number of the length of the two, or n times m, one has length n and one has length m. But again, so I would very much hope that you essentially can say something like that. It's ultimately for me more important that you remember the simple idea how to compare strings than that you remember Blossom matrix. Yes, scoring matrices are important, and you're totally right. Some are more important than others. But the basic idea really at this point is to compare, the first step really is to compare sequences. And as you correctly said, then once you have the sequences compared, you build, so let's go step one back. So you do pairwise sequence comparisons, edit distances. Edit distances typically would be something that just says that an A matches an A, gives an, there's an edit distance of 0. But if I have a different residue, a C there, then I have to switch it. Okay? That looks at identity of letters. There are other ways to measure that take into account the biophysical principles of amino acids. And those ultimately lead to scoring matrices. Scoring matrices reflect the biophysical nature of an amino acid chain, right? This is important for you to remember, not the sentence, but the idea again. Whatever you call it, you call it biochemical features, biological features, whatever you say. But the idea is there is more than just letters, but even if I compared letters, remember what the differences could be when I compare letters? What would be the analogy for scoring matrices comparing letters? Really words, really sentences. Books, yeah?
So it would be the occurrences of them.
Exactly, different occurrences of words. In the letter comparison it would be slightly, well, you could drill it down to the alphabet and say letters occur more often, that is actually true. But the more important one really on the level, maybe on the next level, maybe the one on words. Either of those two. Different languages would essentially have different substitution matrices, if you want to, right? And in the world of proteins, the analogy to that, in some sense, different families may work or maybe align slightly better with different scoring matrices. And now we get into the next point. It's the profile sequence alignment, or the sequence profile alignment. Either way. Would anybody be prepared to talk about what that is? Do you remember what a profile is? Can anybody say it? And again, it is good to not really give the final solution. I could say that myself. It's good that you say something that has some room for improvement in it. Let's call it that way. Anybody? Ideally anybody, somebody new? Thank you, I appreciate it, but I'd like somebody else. Nobody? Profile. The word has been dropped many times. Again, this is absolutely crucial that you are able to say, if you can't say something, why don't you say it now, because you're going to learn for the exam. The understanding should be there today. Ask questions. This is really the word profile, what it essentially means. Okay, let me pick the only one in the room.
Family of similar.
Yes, a profile actually comes from a family of similar proteins. So what you do is you find a family of similar proteins. The way you do that is you do a bunch of pairwise alignments. You do A against B, against C, against D, against blah, 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 against the entire database. And you find anything that is similar to A. And then you put that into a cluster, a group, or whatever you call that. And that is what you call a family. Okay? Now, how do you compile a profile from that? Simply, you take the pairwise alignment and sort of glue them together. And then you know at every single position you can see how many times do you see at that position the letter A. How many times do you see the letter C, and so forth. And that is one way of calling the profile. Now once you have that profile, you can take this profile and go out and compare it to new sequences. Because the profile is more specific than the substitution matrix. Remember, a substitution matrix essentially measures what's the probability of matching an L and a V. Both of those happen to be hydrophobic residues. So matching hydrophobic residues is good. So L and V is actually better than L and E or something, right? That's the biophysical nature of it. So some amino acids fit better to others. Okay? This is just like coupling up in life, like forming loving couples, right? And this is reflected in the substitution matrix, but now once we are on the level of the profile of the family, we have a much more refined version of that. Okay? So that means when I come with my new sequence, I will no longer compare against the typical biophysical features, but now I will compare against what I exactly have observed so far in that family. The larger my family, the more accurate that will be. Since I now have a very specific profile of that family, I can go out and find more distance relations. Let me just switch off my phone. And that is what is meant by this daylight zone here, up here, where you have essentially very high sequence identity between the pair that is aligned, and a simple pairwise alignment with a typical substitution matrix suffices. When you go into this region of more distant, so if the two become more distant, then that is no longer enough and you need a sequence profile comparison. And you go further down, you need profile comparison. So simply you take two profiles against each other. Profiles, again, think about them as a bunch of probabilities. You have a probability at every single position to have A, C, any of these 20 letters. As simple as that. Sequence profile means you align an A against the probability for A. Profile means you align the probability at that position against the probability of that position. And that actually sounds very simple, and conceptually is very simple, but immediately comparing probabilities of vectors, you unfortunately have a bunch of options. You can simply compile the product of two vectors very differently, or look at the similarity between these two very differently, and that makes profile comparisons a little bit more complicated. I said there is no prediction of 3D structure other than comparative modeling, and we talked about essentially the formation of secondary structure. Secondary structure is the macroscopic substructure, the thing that when you look at 3D structures helps you to understand how they look, helps you to visually trace them, and helps you to also somehow see functional elements. There are two major secondary structure elements, and again, I would hope that you would know that: helices and beta strands that together form sheets. So again, a single one is a strand, they pair up, they begin to form a sheet. Some of these sheets have many. In this particular case, you see 1, 2, 3, 4 strands. Actually, it's a bad map here, you have only 3. No, you have 1, 2, 3, 4, 5. But the actual sheet here is formed here. And here's one formed, so you can look on it, formed by 2. What's the difference between alpha helices and strands? And what makes them formed? What stabilizes them? Oh, okay. The answer somehow for the stabilization is here, is hydrogen bonds. What's the difference between alpha helices and beta strands? Well, what's one difference? Can you name some differences? Yes?
I think that alpha helix normally is more locally than
the alpha helix is more local. In the sense that the hydrogen bond formation is here between the residue I and I+4, for instance, while here every second residue has a hydrogen bond, but the strand that it bonds to can be far away in sequence. Okay? All right, so the reach of comparative modeling. So about half of the universe we can reach with comparative modeling. It's a little bit less on the per residue level. So this is on the per protein level. So this sort of symbolizes the pi of all the protein structures. The blue is the fraction for which we have experimental information. And this one is where we can do comparative modeling. About a half. On the per residue level, the numbers are slightly lower. I said, again, in this image here, 3D structures, 3D coordinates, 2D are the contacts, and then we get down to the string level. Secondary structure is a string. You can write it as a string. You can, for every single residue, write H, E, or L or something like that, and there it becomes a string. Often in the literature you would find it as something secondary, so people can somehow, second sounds like 2D. And there's a total confusion. Secondary structure is a string in terms of information content, no matter what the literature says. Again, in DSSP has different states of secondary structure. The major ones here are helices, and they differ simply. So I said I and I+4 is a helix, so some helixes are a little bit wider and some are a little bit more condensed. The pi is wider, the 310 is more condensed. These are extended, essentially is the beta strand, and it's called extended because you don't wind up, it's just a stretch. Even the ones that are not helices, not strands, typically are not for that long stretched or elongated. That's historically why it was called extended. Beta bridge here is simply a short stretch. And all the others typically are referred to as other. Over the course of the lecture, I will often use the word loop. There are many words out in the literature, coil and all of these other words. The important part is helices are defined by hydrogen bonds. Strands are defined by hydrogen bonds. Everything else is unclear, is not well defined. And other would be the right term. Now, when we look at stretches, consecutive stretches, so-called peptides, then sometimes we see, and this is an old paper here from '85 from Kapsch and Zander, we see that these long stretches always are observed in the state helix. These always observed in the state strand. This is other. And some pentapeptides, 5 mers here, are observed in both helix and strand. Okay? Our question to you, how could that be? How could 5 mers be observed in strands and helices? So pentapeptides, again, is 5 residues. Penta is 5. Any idea, any suggestion? So I have the same stretch of 5 residues. Sometimes it's a strand, sometimes it's a helix. or to stay in the, sometimes the helix, sometimes the strand. Any idea? Any suggestion? Think about it. How could it happen? Yeah? Exactly. So the answer is environment. That means depending on where in the structure you sit. Let's just look at the simple case. The beta strand needs a pairing, right, to something else. Now, if it doesn't find any binding strand, maybe this is going to wind up as a helix. Or at least part of a helix. We have seen some pictures like that. However, when it does find a binding partner, then it can pair as a strand. So in an information content sense, what you would argue is that for these pentapeptides, 5 is not enough. It's not enough to decide on whether they are beta strands or helices. We need something longer. Now on this graph you see that at least the helices and the strands that are unique to this blue and red happen mostly to be longer, so there's an exception here. But most of them indeed are longer. But again, let's look at the hydrogen bonding patterns. So helices are more local, strands are less local, so maybe here we need longer stretches. What is the simple method to predict secondary structure? Can you invent any? So secondary structure, I want to predict from sequence 3 symbols, H, E, or L. Again, other, the state other, we will just refer to L because of historical reasons. So I want to assign every single letter, every single amino acid in a particular protein to one of these traits, H, E, L. I cannot, for my sequence of interest, look up the database of experimentally known structures. Because if I could look up the structure, then I could do comparative modeling and I could predict the 3D structure. Secondary structure I want to predict for the remainder half of the proteins for which I cannot apply 3D structure prediction methods. So I cannot look up anything because by definition that lookup failed. Okay? So we need some other method. How can we do it? Why is it that I'm so much over your heads? I do understand that this is 2 weeks ago, but we had a chalk talk in which we discussed a couple of ways of doing that. And I understand it was not on the video, but how would you do it? Think about it. And again, so in some sense, what I would hope in the exam that some of these questions may face you with ways of looking at it that appear new to you. But it's a simple problem, right? How could you do it? Give me any idea. Yeah?
You can compute the probability from the HSP, which residue will lead to helix or strand or...
Yes. Let me just, this is not quite that one. So the one that I show, okay, I'm not going to repeat your solution for a minute because the next one, over next slide. So the simplest method somehow that was sort of induced or indicated by what I showed before is take a known structure, find the longest consecutive run of motif, of sequence, of word, if you want to call it that way, that you only find in helix, only in strand, only in something else. And you have the simplest secondary structure method. The problem with that method, of course, is, well, often you will not find that particular stretch. Okay? If it is long enough, in the longest, in the extreme sense, again, if you think about science, always think about extreme. Very long motif would be one that is as long as the entire protein. Now, by definition, it doesn't work anymore because already I said I don't find the protein sequence in the PDB. Okay, it must be much shorter than that. If it is too short, again, we know it doesn't work. So somewhere in between it may work in some cases not. We already saw 5 mirrors is not long enough. When I get much longer, I get too specific and I miss many things. That's the problem. So I will have a secondary structure prediction that maybe I have 100 residue protein, and maybe there are some regions where I have a prediction, but most I don't. And the simplest method is actually much simpler, and the first one came from Shen-Gurji in 57, that is before the first experimental structure was actually seen. And that came from a simple feature, an observation, a simple feature of the amino acid called proline. Proline bends the chain. So as you correctly observed, the folding of a structure, of a protein sequence into a structure, you have 2 backbone angles for every single residue that can change, that can rotate, that are free. Now proline, it sort of reduces that degree of freedom. This is why proline often breaks a helix. Now if you know that proline breaks a helix, you already know that before it, you see a proline before it is a helix. That's the simplest prediction. And to some extent, it works. And now this brings us to exactly the idea that was formulated here, which is to go from proline to odds for all. And the odds for all was, that's what she said, you simply take a protein sequence, you look up for every single residue, what's the probability to be in either of 3 states. In this particular case, the protein has only E and L. So all of this, the H would be 0 here. But, so again, the count, you simply take the D is 1s in the L, again, the E is 1s in the L, and so forth and so forth. So you, for every single residue, you ask in that sequence up there, how often do you observe the D, the Q is in an L, the E is in an L, another E is in the E, that is this one here, right? And so forth and so on. That builds a probability matrix. You do that for all the proteins that you know. Once you have done it for all the proteins, this matrix gives you a probability for every single letter. So now even if you don't find your protein in the database anymore, since you have a probability for every single letter, you have a prediction. The next issue is how do you use that prediction? And in the simplest way, the prediction would be used by simply saying at every time I see a D, say that would be our final matrix. Every time I see a D, I call it L, because that's the highest probability. Here I swap a coin, here I call it L, here I call it E, and so forth. That's essentially, you take the highest probability for every single letter. What's the problem with that? What's an immediate problem with that? An immediate problem, I indicated, say my 3-state H, E, L for the letter V would be 0.4, 0.3, 0.3. So the highest probability would be V in a helix. And what's the obvious problem with that? Can anybody see that or remember that? Or think about what the problem is? Yes?
One problem is that V is not always in helix.
Yes, that's true. Not only is it not always in helix, it's even more extreme. The way I constructed this example, yes, this is the max, 0.4 is the max. But the non-max sums up to a higher number. The max actually does not even take half here. So the probability not to be in a helix is 60%. The probability to be in a helix is 40%. So by picking this particular residue always in a helix, actually most over the entire chain, I'm actually mostly wrong. Right? And that is a problem that is on this level not easy to fix. Well, one hack would be that you sort of make sure that you get the probability distribution over your sequence. But that really is a hack. Because just because you, for the first V, you take the H, and then you know that the probability distribution is such that next time you have to take something else. But this is totally random, right? You could start at any position, you would get a different distribution. It's completely, well, okay, you could sample all possibilities and see whether you could do an average of all possibilities. That would be actually a slight advance over that. But you see that it's very simple and somehow restricted. The methods that were published that in fact had that idea were published from 57, that's the Proline, only to actually the 70s and 80s. Chow-Fassmann is one known method. Gore is called after Garnier, Osgothorpe, and Dropson. So those three authors here. How can we go up from that? How can we essentially, we look at a probability for a particular amino acid to be in one of the secondary structure states. Well, actually one problem is where do we get the secondary structure from? We talked about that, that is DSSP, and that was already the answer. Let's go to the next issue. In fact, since I have the secondary structure assigned, I can measure how good those are. How would I measure secondary structure prediction methods? What should be a measure for the success of a prediction method? Any idea? This is a very simple question. Just come up with a handful of solutions. What could you measure? I want to see how good my prediction is, yeah? Sorry? No. I'm really asking about a value. Not a procedure. You're giving a procedure. I want a value. How do you, what are you going to measure? What's the score?
What we predicted is, if we predict it as a helix, is it a helix or not? Cumulative error, basically.
So, wait, not too fast. So now we have one. What we predict as a helix, is it a helix or not? How do you put that into the algorithm? What do you do?
The cumulative error cross, like if you if you predicted it to be wrong or the false positives and false negatives, we just sum it up.
Okay, yes, that is true what you say, but I want to be more explicit now. Say that is L, L, H, 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 L, L, and that is the observation. And my prediction would be L, H, 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 L, L, L. 1, 2, 3, 4, 5, 6, 7. Let's do two more. L, H, H, L. Wait a minute, two more. L, H. Okay, 10. So, throw some ways to compile numbers at me. So the suggestion is I want to see how well I predict the helix. So how well do I predict the helix here?
Number of correct suggestions as percentage of the total length of the helix.
So the number would then be here. What would be the number?
Here the number of incorrect ones is 1, 2 incorrect, and the rest seem to be correct. So
okay. So you could 80%
correct, 80% accuracy.
So this is an interesting way of doing it. So you say we have 3 and we have 2 incorrect.
So we like comparison.
2 are right. So how do you get to 80?
The rest are right. 2 are incorrect, the rest are right. So as a
2 right, 2 wrong. So how is that 80?
2 right.
So this would be wrong, this would be wrong, and these 2 would be right. So there are different ways of counting, and that's what I'm trying to get you into. Yeah?
You attach a positive.
For the whole sequence, we see how many correct predictions do we have and how many wrong predictions.
Okay, so that's the simplest one. The so-called Q3, a 3-state accuracy. So for every single residue, I count, is it right, is it wrong? And then I simply look at the percentage of all right ones. Okay, Okay, and is it 3 states because there's an E usually. But before you said something else. So that is one measure. And before you said, how accurate is the helix? And let's get back to that helix issue. In fact, since what we are wanting is to predict helices, this may be an important issue that I actually do not really look at the per residue, at all the residues accurately, but I look separately at particular states. It could be that I look at helical residues. And again, there are different ways of doing it. In the approach that was started here, we somehow have a sense of a unit, of a segment. We're not really completely looking per residue. We are saying, okay, this is identified as a helix. Helix has 3 residues. How do I measure whether that helix is correct? Back again to you. You said 2 incorrect, 2 correct. So what's the score?
Could we maybe attach a positive value to the correct and somewhat discounted by a negative when it's incorrect or something? Sure. Like a weighted...
you can do all kinds of things. Please give me an answer that is specific here. How could you do it? Yes? Sure you can do that. How? Okay, it's somebody else. Yeah? Oh, yes, we could do that. But now you're ahead of the level of complexity. So, yes, we could use a Markov model to simply look at the probability of the agreement between 2 strings. But this is really, again, yes, we can use hidden Markov models to align protein sequences. And that, by the way, would have been another sequence alignment method, where you essentially replace the scoring matrix or the profile by the hidden Markov model. And we could apply that here too, but it's way beyond the level of complexity into which I want to get. I want to have a simple number. I wanted you to invent a few simple numbers. So much simpler than putting a Markov model on it. Just count. And indeed, yes, you're right, you could do it in different ways. And what you describe with your words sounds good, but I want something that I can compute. That I can put into a formula. Any idea? Throw something at me. I mean, an idea. Nothing physical. No tomatoes. Well, come on.
The position maybe, is the position matter? So if the correct matches are at the 3rd and 4th position, or maybe the scoring matrix scores of H and H matching, minus the score of H and L, scoring matrix score of H and L matching?
That is a good idea, and it's again, but you're getting, in some sense, you're getting back to the same, you overfit the problem in some sense. Yes, since we look at scoring, so similarity in structure, so secondary structure relates to structure comparisons. We can learn from structure comparisons whether an H has a probability fit to an L, and that would get us into a Markov model, or would get us into a simply scoring matrix for H and L. I want to stay away from that. Yes, you could do that. And in fact, we have done that. But for the beginning, let's make simple steps. And over the course of this lecture, we will not get into that level of complication for this problem. I have 2 strings, I want to compare them. And these 2 strings are not, I'm not moving around. This is one prediction, right? So there's no alignment problem here. The prediction method says, this residue is a helix. Not that one, not that one, not optimize the helix overlap. This is the prediction. How do I measure that? Again, one solution is of essentially the edit distance, if you want, of all percentage of residues that are correctly predicted. Give me something else that is helix specific. Okay, let me give you something, and this is not what I want, what I'm hunting for. You could simply compile 2-state accuracy for helical residues. Same as before, but for every single residue, just look for helices. And you ask for all the helical residues, how many did you get right? That would be another measure. But I really want something that's sort of acknowledging the fact that there is a helix. And again, any idea flies, just give me an idea. And there's so many things, so many ways in which you could do that. No?
like this probability will be 2 over 5. Is there 4 going
So one way of doing this is simply to argue, okay, I have 2 correct ones. I have 1. Why is it 2 over 5?
2 over 5 is there 4 right?
So I believe we have 2 correct ones. And why do you want 2 over 5? 1, 2, 3, 4.
L to L.
This L? I'm making mistakes, what you're telling me? So, wait a minute. It's 1, 2, 3, 4. There's no, so here I get a helix, an H residue too much. Here I'm missing 1, but the whole stretch here is 4. Where do you see 5? There's something I don't see. Is it? Because there are 2 people in the room at least who see that. These 2 people, can you help me out? I don't see, I only see 4. So I could say I begin counting here where I'm over-predicting, and I could count to the end of where I'm observing, so that would give me 4. So that would then give me 2 in 4.
No, actually, I'm counting the matching letters.
You're counting the matching,
There are 2 helix that are,
but it's only 2 that match.
and there are 2 L.
Ah! Oh, I'm sorry. Yes. But, so again, okay, now I get your point. In fact, that is a different way of doing it. And it's an interesting one. And I don't want to get into that. Because I still want to sort of explore a little bit more of the simple space. In the simple space, I have an observed helix that is 3 residues long. And I want to see whether I map that helix. And one simple way is to say, okay, of the 3 that I observe, I get only 2 right, 2 of 3. Another way of looking at it is, okay, I count this also as a wrong prediction. Because in sort of a probability landscape, over-prediction has to somehow be penalized. And that actually is a very valid idea. It makes it a little bit more complicated, because then you have the optimal is a sort of swimming target. You no longer, so the more you over-predict, the smaller the makes sense. So then you would essentially say 2 in where it starts to be wrong predicted to end the wrong, so that would be 4 or 50%. Yeah.
Can we do it also like if we start at L and H, the wrong prediction,
yeah,
then the probability of me predicting it as H instead of L, and it actually being L and into a negative score, plus the probability of me predicting as H and actual it being a correct result, actual real being H, plus I need to.
I challenged you before. Give me the number. You have something very complicated in your head that I don't get, but give me the number for this.
Is it like 50? What's the
50. So that's what I meant.
So
it's 2 and 4. If you give me a different number, then explain the different number. Think about it. Okay, so you immediately see these 2 different ways. And another way, we could have sort of a 2-way look at it. So we could argue, well, how many of the ones that are observed are correctly predicted, but we could turn that around. How many of the ones that were predicted are correctly predicted? So how many, so say here the misprediction was longer here, then we would say, in fact, here is 2 of 3 in one direction of looking at it as percentage of observed. The helix is 3 long, 2 are matched, 2 of 3. Here we would say of the predicted, only 2 and 4 are right. The whole thing is 4, and of these only 2 are right. So these are asymmetric ways of looking at it, and they both carry different pieces of information. So in the first way, for instance, of just focusing on the observed helix, this incorrect prediction would be completely ignored. And the probability scale, again, this is maybe not quite the right thing. Another way of doing it is to come up with a simple threshold and say, well, as long as my helix overlaps for 50%, 60%, 70% or something like that, I call it right, and I have a binary count system. How many of the helices do I by that threshold get right? And all of these kind of measures have been used and have their validity. And then there is the most important one that is in computer science typically a 2 table, but in this case it's slightly more complicated. So I have observed 3 states, H, E, L, and I've predicted 3 states, H, let's just label them with a P and an O here, H, E, L, predicted, and then I simply count how many are predicted and observed as a helix on the level of a residue, how many of the ones that are observed as a helix are predicted as a strand, and how many are observed as a loop. So I get these 9 numbers, and I can compute out of this table of 9 numbers, for instance this number, for instance that number. I cannot compute the segment scores, because this number just chops it up into single residues, okay? And anything that you can compile for single residues is contained in this matrix. And you can essentially, and this is not that trivial, but you can write an information index for that matrix. I mean, you can do it in many ways, but to create one that is completely symmetric in these residues is not that simple. And all of these measures tell you something. By the way, there's another one that we will also get back into the lecture. So we could simply look at the length distribution, absolutely ignore whether I get the helix right or not. Simply ask, how many helices do I predict of a large data set of length 3, of length 4? And are these 2 distributions, the one observed and the one predicted, similar? So then I could score very high by completely never getting any helix, but at least the overall distribution would be right. And that is yet a different measure. Okay, so let's just look at a typical prediction here. That's the one. And now the Q3 is easy to compile. That's what we had. Okay, in terms of Q3, initially they published 63% accuracy, but using BSSP, it turned out this is more 50 to 55. I tend to call that the first generation of method. The simplest thing that you can do is look for a probability of a single residue. And we immediately saw in this class, and it's all, I hope, obvious to every single person in this room, that this is already, has problems. So how can you step up from that? Yeah?
So you can take several residues, like 3 or 4.
Exactly. Now you can look at correlations. So you no longer say, what is the probability of the proline to break a helix, but now you say, what is the probability of the proline to break a helix if it sits next to a leucine? Okay? So you're looking at segments of consecutive residues, and you're compiling a conditional probability. So in the conditional probability, essentially you compile the probability that this is in a particular secondary structure state given its local sequence environment, its local amino acid environment. And the methods from this second generation GOR3, and I had it on the slide before. So here are a couple of the major methods that sort of push this field in the beginning. It gets to levels of accuracy 55 to 60%. Now, the problems with these first generation methods is, well, one problem is that they are not 100%. Many methods were developed, and none of them ever claimed anything more than 65% Q3. So people argued that this is the theoretical maximum. Yeah?
Wow, how do you arrive at 65% number?
So that was the highest. Again, it was an overstatement. Actually, those days they did not have enough data to really measure correctly. So what I call here 55 to 60, they thought was 65. And no matter what the people did, is they ended up at 65, or it's something that today I would say is 60. And then they said 60 is the max. I mean, the publication said 65 because they saw a higher number.
By experimentally trying it, they found it out, but it's not theoretically proven that 65 is upper limit.
So no, that's exactly where I'm going with my question. So the statement was, we have found no prediction method that gets a number higher than, again, historically the statement was 65. It should have been 60. And because we find no method that reaches a prediction accuracy higher than 60, this is the theoretical maximum. That was the statement. What comes to your mind if you hear that statement? In fact, again, this is not only one person. It was published many times and published by people who were really, really intelligent and knew a lot. So why not?
Always be a smart guy.
That's sort of, let's call it the safe way. There's always going to be somebody who's smarter than that, and there's always going to be a solution. And I believe that's sort of your lesson learned from life, point taken. Can you be more specific?
Does it have anything to do with the 66% standard error computation?
So no, it doesn't have to do with standard errors. And it doesn't have to do with estimate accuracy. But let me ask you differently. Do you have any idea what they may have argued, why there could be a ceiling, why there could be a maximum? Are there things that come to your mind that would somehow define a ceiling? Let me turn that around and remove it from secondary structure prediction for a moment. So what's the limit of what I can achieve in terms of secondary structure prediction? Can you think about the definition of the limit, not about prediction methods? Really, the limit comes from somewhere else. The simple limit comes from somewhere else. Experimental resolution. So you cannot be, in your prediction method, you cannot be more accurate than the experiment that creates the data that you actually used. It's very, very unlikely, at least. Maybe you can. There is always something in life. I take your point. But it is very unlikely, right? This is one simple ceiling. Another way of defining a ceiling is to say, okay, comparative modeling means I find a protein that is similar to a protein with an experimentally known structure. If I do find that, I can predict 3D structure. I don't need secondary structure. And in fact, that I expect is much more accurate in predicting secondary structure. What I want is a prediction method when the other method doesn't work. So most likely, actually, comparative modeling is also a ceiling. So the degree to which residues are similar between proteins that when I look at their structures, I say they're identical. Essentially, identical structure means identical secondary structure. Okay, that's another way of a limit. And maybe they differ a little bit at the ends. So there are some minor mistakes, and maybe this is the utmost resolution that a prediction method can get. That number would be in the ballpark of 90, by the way. But there's something else that could be the reason for an upper limit, wherever it may be. Any idea?
Regression accuracy?
No, regression accuracy. Now you think too much in terms of yeah, that's in some sense. So again, how do you mean that?
Like if they tried predicting and then they tried fitting a regression line and the beta, like the accuracy which R you get after regressing.
But again, so what you're saying is, I have data, I try to fit my prediction method to those data, and then there is a mistake in my regression line. But that's the prediction accuracy.
Yeah, so like they might have tried the methods and then compared to the actual results, and they saw that in general the regression line they predicted had like the R square on a 65.
Yes.
And that's the maximum they could reach.
Yes. So essentially, what your colleague says with different words is there is a limit in prediction accuracy. The question is why? What you describe as a limit in prediction accuracy.
Why?
Just you like the word regression. I'm not blaming you for it, but it's not an answer. Any idea what people would argue? It is something biophysical, and it's something that has to do with features of secondary structure. And it's something that the last time I asked it today, the answer came from somewhere here. So can somebody from somewhere there give out an idea? No? Oh. So it is ultimately related to the idea of locality. So I have a window of consecutive residues. What if secondary structure formation is not determined by that window? What? We already saw the 5 mirrors that didn't work, right? Now, okay, for my probability curve, I can go further. I can go maybe to 17. But what if the limit of secondary structure prediction is exactly the limit of what is locally defined. Okay? Now, there's another observation in these in the second generation methods, which is that strand is predicted at levels below 40%. So in a three-state system, 33 is sort of random. That means the accuracy of predicting strand is very close to random. And again, this fits very well with this explanation before, because strand is less accurate, is less local. The formation of helices is local. The formation of strand is not, and maybe that is exactly the problem. I don't capture secondary structure formation when it is imposed only by long-range interactions that I don't see in a window. Okay, now, so just back to the statement here, strands are not longer. Okay, how could I solve that problem? I could make the window as long as the entire protein. What's the problem with that?
It could be too long.
It could be too long, why? Say we look at a window of 100. Why could that be long? What do you mean by to measure it? You can always look at the probability distribution. You can always measure. But what could be the problem?
The errors would accumulate, right? If you have a very large window.
Ultimately, that is very much the point. So, for every position you add in your window, the longer your window gets, the more you will have some noise. And at some point, the noise, the errors, will take over. So yes, very far apart, there is a connection between the two. But there's a lot in between that doesn't matter for that. And finding which one, in the ocean of noise, the signal disappears. Okay, that's one major, in fact, that is the major problem of making windows too long. Another technical problem would be, I asked what is the problem with the entire length. Remember, proteins have very, very different lengths. So then we would have a secondary structure prediction measure for essentially every single protein. So that there's another very trivial problem. But ultimately the problem really is you get lost in the ocean of noise and error. So it doesn't help. It doesn't work. Here's another problem, the problem of short segments. What I mean by that is in a typical prediction maybe like this. So this up here is the observation, and again I'm sorry that I should color that in red here, is HHH. And that is a typical prediction. Now in this particular prediction here, you see that in this particular case, and even in that case, let's begin here. Most likely a human reader of that would say, okay, this is a long helix. This E is either a helix or the other state. By the way, the other state is just a blank here for visibility. So this is just a long helix. Now here, well, it's getting more complicated, right? It's still a long helix. Here, well, is that a long strand? And immediately in this particular case here, it's difficult to see because I forgot to make that red here, but you would immediately see that turning these two H into E would be wrong. So here in this particular case, these two H are actually right. And all the other cases, the short ones are wrong. Actually here, this short one is not wrong, the longer one is wrong. But what I'm saying is if the segments are predicted too fragmented, too short, then the usability of the interpretability of the prediction gets complicated. Even for 50%, Q3 50% with short, incorrect length of segments. So you can reach 50% of getting some helices right, and you can reach 50% almost never getting helices right. Always sort of half-half, and you don't know how to use it. And that's another problem. So the last 15 minutes, because before we continue, let's just introduce the concept of neural networks. Who in the room has seen neural networks before, yeah?
That's a question for like, so if you have two methods and one of the two has higher accuracy, do we always choose the one with higher accuracy?
So the question is, if we had two different prediction methods, and one has a higher prediction accuracy, will we always choose the one with a higher prediction accuracy? And that gets, the answer to that question gets me ultimately exactly back into the reasoning here of there are different methods of assessing prediction accuracy. So say one had a much better Q3, so overall more residues are correctly predicted, but the other one would at least get this strand and this strand right. Many things in between wrong, but at least something that is absolutely right. which one would actually be better. So often we would choose the one with a higher Q3, and we would ignore that there's another there that has a different criterion by which that one is better. And that is exactly why we actually need to look at different features. And I'm going to present a few different looks at different features or examples how looking at relatively simple ways of different features helps you. Overall, the design hope is that I can optimize a method to solve many problems. Yeah?
I was just asking, like, can't we take like an average of the window sizes and take a different window sizes and see which reduces the most error?
Yes, so indeed, when you develop a method, so let's get back, I said before that making the window too long, too much noise, making it too short, too little information. There somehow is a payoff in between. How do you find that payoff? You simply try in a prediction method all the window sizes, and you hope that there is an optimum, and that's the one you pick. Right? You could also imagine that there is not clear optimum, and then you average over different solutions. And again, there are methods that do exactly that too. Okay, so let's get back to this issue. Who has seen neural networks before in lectures? 2. There's relatively 3, 4, 5. Still a very limited number of people. So what I'm going to introduce here is the particular simplest type of the so-called feed-forward networks. And this is essentially a very, very simple concept. So you have units. And this is the input here on the left-hand side, blue. Here's the output in green. And there are connections. The inputs have states. The connections have states. The J's have states. What you do as an operation, you begin by multiplying the vector of the input value, 1, 1, with, in this particular case, the vector of the connections, 1, 0. Simple vector multiplication. More at the molecular level, what you do is you take the value here, 1, multiply it with the connection, 1, and that's what comes into the green unit. Ultimately what that means is, in the interpretation here, you multiply two vectors, so you project one vector upon another. In the next step, when you decide what will come out of that unit, you now apply a decision. You apply something that is translating the vector multiplication. So the vector multiplication ultimately is the projection. And in the next step you want to do something that is asking, is it longer than something or shorter than something? Some threshold. And the simplest threshold would be a sigmoid here. No, it's not simplest, but the simplest is a step function, but there are issues with step functions. So a relatively simple step function that you can analytically handle easily is the sigmoid. For instance, hyperbolic tangents here, that is such that when you have very, very large negative values coming in from these two products here, then you switch to 0, very large positive, you switch to 1, and something in between. Okay? Very simple. What's the free variable in my game here? The input is given, and typically these are supervised. Supervised means I know the answer. I know the system somehow should learn a classification that I have from experimental data. So what is it that I can change in my system?
The weights, the connections.
The connections. So the free parameters are the connections. In this particular example, I would have 2 free connections. And training the system would simply adjust the connections such that I get the right output. To begin with this one here. Say, and I'm sorry that is so not strong enough here, but 1.0 is the dark and the light. And I wanted to sort of classify these two types of points. Say I began with my system like that. I have a certain initial choice for these connections. I do the product and I get an output. I know what I want. I square the two to get sign independent, and then I have a mistake. Now, in the space of error versus the connections, again my free parameters are the connections. That's my error. In this space of error versus free connections, I'm going to go downhill. Going downhill would trap me in minima. So I allow some jump above A gradient descent means you essentially allow yourself to jump over little hills. And at some point, maybe the hill will become too big. Okay, so in this particular case here, so 1 times 1 plus 0, this is close to 1, here is the other way around, so you want to switch these connections, so you essentially you present samples at every single, my time is running out to really go through this example. But what this example shows simply is counted through how you, in the next step, change the junction, how that corrects, how that changes the error you make, how that induces a new change of your junction, and you do that stepwise. Okay? When you do that stepwise, then ultimately you can classify these points by lines. Vector multiplication essentially introduces a line. Line meaning larger, less than some point, right? I have different classification lines here. And again, this is, that's light, an open circle, dark circle. You may not see that. Is there anything different between the lines I show? Yes, they differ. So they are different lines. There's a different descriptor of a function. Is one of them solving the problem better than the other?
Yes.
Yes? Which one?
The one which is tangent to both circles.
The one that is?
Tangent to both circles.
You have to help me, my ears are not good enough.
The one tangent to both circles, maybe?
I still don't get it.
The one tangent to both circles.
Oh, this one here.
There's another one.
This one?
Yeah.
Okay, I would argue, I do see points why you could argue this one. I do see arguments why you would argue this one. I do see arguments why you would argue this one. Ultimately, for the problem on the whiteboard now, there's no way to distinguish that. They are all equal because they all give 100% accurate classification of the data points I have. I do not know how my future points will fall. From the set that I have on the whiteboard here, you cannot make a distinction. They're all equally good. You may argue that, again, so you can argue for this one. Some would argue for the SVM would try to put this line in here because it would somehow stay equally far apart from any point that they have. It's called a line of security or security margin. But ultimately the problem doesn't define that, and the answer is they are really, according to this problem definition here, equal. Now, what about the left one? Oh, sorry, the right one. How can you classify those with a line?
You can do it.
You cannot, is the answer. Does anybody disagree with that? This so-called XOR problem, and when you do Google, you will immediately find that you cannot separate that with a straight line. But I never said anything about a straight line, did I? Think about outside the box, right? You can. But, okay, my neural network, the way I described it, does not do this. The neural network that I showed you so far, the simplest one, input-output layer, allows you to have simple lines, and what you can do, you can classify it with 2 lines. How can you get 2 lines? Well, in the simplest way, you introduce what is called a hidden layer. Hidden layer is called hidden layer because this is input from the world, this is output into the world, and in between is just a computing layer. This is something that does something. The way the computation works is just the same as before. You take the value of this one, multiply it with a connection, that's the input. You add the same product from here. The output, that's the addition here. Then you have a sigmoid function. That defines the output here. You multiply that with a connection here. You do the same here. You sum over these 2. And that's the input here. You apply again the sigmoid function, and you get the final output. You somehow simply repeat the same thing as before. Nothing new. Again, in order to train, you go essentially, now you replace the simple vector idea by a hyperplane. Now you find essentially it's the same idea as in the SVM. In principle, you project your problem into a higher dimensional space, and now the solution you find is no longer a line, it's a hyperplane in this higher dimensional space. And again, you have a simple output error. that you define, and the free variables are the connections that you will go downhill in the error space. When you go downhill in the error space, then over training time, you may observe that you increase your performance. And what could the blue one mean here? I believe that was right. Yeah? Did you say it?
I'm not sure.
Also,
It is accuracy.
the blue one is accuracy? No, the accuracy would be somehow this, in some sense. But I have a green line and a blue line, and they have different behaviors. What could that be? Could be two different methods. Not the case. For machine learning, this is typical.
How much the marginal learning, like how much?
Yes, and in fact, then typically there's this word of overtraining, and the way of overtraining, by the way, this is a toy problem. This means typically the test set, and that typically means the training set. Test set, the word cross-validation was already mentioned by you. The test set is something that I leave out. So I have 100% data, say 100 proteins, and I, for instance, take 50 for training and 50 for testing. So while I while I train on the green line, I never test on the blue. And then, or in this particular case, I do test while I'm training here, and I see that at some point I reach the optimum. That's the point when I overtrain. Overtrain, overfit. Ultimately, it means that the solution you find is only valid for your training set at this point. You no longer extract the principles. You no longer extract any generic rule. Okay. So that comes from cross-training or testing. In reality, you do not have it that way. In reality, and this is from a real training neural network or secondary structure prediction, how that works I will tell you next Tuesday. That's the Q3 for the training, and that's the Q3 for the testing. You do see there are points that are highest. So it could be this one, it could be this one, it could be this one, depending on your error estimate. So numerically, this is the highest value. But most likely, you overtrain here. Most likely, somehow here or here is the point beyond which you overtrain. Compared to the toy problem, so you see an optimum, you see the effect of overtraining, but it's nowhere near as it is typically discussed in toy problems. Real life is usually much more complicated. With that, I leave it. We will continue here on Tuesday. Please be prepared with some questions to that. Thank you for your attention.